Okay, welcome, people of Earth, to day 15 of Advent of Code. Um, we've got about 5 minutes before the puzzle opens for tonight, so let's look back on how day 14 went. Um, just in terms of, we have complained about parsing a lot. Um, One thing that I think went very well on day 14 is splitting out the first line that had the initial string from the rest of all these rules into, one I just put in a variable in the file, and the rest I read, but it was all homogeneous. It was a pretty straightforward parsing operation, so it only took us a couple of minutes to get the data parsed. That was a big improvement, and so maybe we have learned something, or maybe we just did well on that day with parsing and it's going to be a disaster going forward. I don't know. Um, the the major bug that we had with the first part was. Hold on, let me wrap. No. Sorry. The major problem we had with the first part was that we weren't computing our pairs correctly because my slice operation, a function that I wrote myself, I had forgot that it didn't include the close here because I initially written it as an inclusive range. Watching the video, I realized I wrote the print statement to display what the pair was as soon as I wrote that, and I just never actually ran it. And by the time I did run the code, I had deleted the print statement because I had moved on, because I had assumed I had run it and seen what it spit out. But, so I guess there's a lesson there. This whole thing about just every time you write a couple of lines of code, go ahead and run it and, look at the output, if you put print statements here to check that the new code you've laid down does what you expect. That does seem like a good way to avoid bugs. Whether it saves you time in the long run really depends on how accurate you are as a programmer. I guess if you really want to get very good times in these competitions, then you just have to write your code with no bugs at all and then don't waste any time testing it. It's probably the way to get a good time, but I'm not particularly good at that kind of programming, so whatever. This was the first day of this thing where the algorithm for solving part 2 at least, it was not immediately obvious to me. I really didn't know what I was doing. Watching the video, so I spent 3.5 minutes kind of looking and trying to identify patterns and anything. Then I had to sit back and really think, and it only took about 2 minutes of just reflection and thought to come up with what was essentially the strategy that got me to the finish line. I think that's perfectly reasonable, but it's good to remember that it does take some time. It does take some thought. It does take some reflection. Not everything can be immediate, which I often forget because I expect to always know the answer, but that's not how it always works. There was a lot of kind of nervous program energy because I was being very myself last night. And part of that is because writing non-trivial logic is genuinely fun. I really enjoyed doing last night's problem because, it wasn't entirely straightforward for me. I did have to think through what I was doing, and it wasn't just coming up with a nice code structure for logic that was obvious, but the logic was a problem to think through and work through as I built the code around it. And I enjoy that, right? We did discover, how are we doing on time? We got a minute left. Did discover because I didn't ground my recursion, so we blew our stack with just an infinite recursion depth. It turns out if you try and do that in LLDB hangs trying to backtrace one of those blown stacks. Maybe LLDB would have eventually gotten there, but it's not very smart about giving you some kind of, you're just repeating this thing. I have seen this behavior in debuggers before, which is why I kind of suspected that was what's going on. But that's how you learn those kind of symptoms is you see them. So when LODB does that, you probably have an infinite recursion. Um, anyway, we're about to open. Oh, save that. Open day 15. So let's move on and see what today has in store for us. Okay. Okay, top left. Okay, only Manhattan moves. Lowest risk total. Ooh. Um. Okay, let's get our input here. I was thinking, oh, it's big, but not. Is it? It is big. Yeah. Well. Okay. Um. So, how big is it? Let's. Oh, God. I hate this. Okay, so we did get our digit grid. Okay, so what are we doing? I mean, if we had a real shortest path graph algorithm, I mean, I could write that, but that requires some stuff. We have two possibilities. So we know we have. Okay, let's actually compute this. G count G0 count. So what are our dimensions here? So it's 100 by 100. So we know we have just 200 moves, but there are two possibilities for each one. So there are two to 100th possible paths. That's not a good approach. Um, ugh. No, there are. Sorry, we need. Uh, we just need an ordering of the. There, it's nothing like 2 to 100th. Are there few enough though, so we can go down or across? And if we make 100, it's less than it's less than 2 to 200th, but it's still a lot. So, do we have to use a real graph algorithm? Ugh, kind of don't want to write that. Um, um, but maybe we have to. Yeah. I'm gonna have to resort to Wikipedia to remembering my shortest path graph algorithms. And these are edges versus nodes is all a little confusing in this example. I don't want to do single source. Is Dijkstra the right one? Unweighted. Yeah, I guess this is it. Oh no, come on. Algorithms, Dijkstra's algorithm. This is the right way to do it. What is the pseudocode? Okay. Okay. Equals from 0.2 v x v y plus 1 vx plus 1y. Oh wait, hang on. The shortest path. No, it's all in VM neighbors. Yeah. Distance u equals d's of v plus digit grid of p, right? Ba-ba-da-ba-da-ba-da-ba-da. Less than d's of p, then d's of p okay. We're being slow again. We could have done this a lot faster. Even this fairly general solution. And then p's of p. Equals p's v plus v. Okay. Ba ba da ba da. Okay. And then we have the shortest path to get everywhere. So now we need to initialize things correctly. So that's the initialization to infinity. Previous is, oh no, let's make this just previouses, I think. Okay. And why for each? Oh, still in queue. For each neighbor still in queue. So not visited. I don't like the way this is written. So D's 0.200 is zero visited insert while okay, the whole queue thing is a bit nonsensical, isn't it? For G, and what is it? Grid? As grid? Okay. If P. Oh, this is a straightforward algorithm, so it's actually not terribly interesting to code up. These digit grid what? This is a, did I make it a subscript operation? Is that what it is? Yeah. Digit, no, G. Yeah. Oh my. No P. Missing M. Okay. That's line 19. Okay. D's. And are we always going to hit a neighbor first? Yes, we are. So let's try just force unwrapping that. Well, okay. We did something. D's of 99 maybe. Oh. 408, yeah, well, but we should read the problem description to see what we actually want. Total risk. What is the lowest total risk? Top left to bottom right. Yeah, okay, so the claim here is that it's 408. D plus GP, yeah, 408 maybe. I don't know. Oh, sigh. Yeah, great. Oh, fine. So here, let's do some samples. Okay. Let's print P's. Print D's. Oh no. Oh no. What happened here? Found nil. Oh, because we're going to 99, right? And we actually want 99, I think. Is 40. Oh, the starting position is never entered, so its risk is not counted. Read the problem. Equals 0. Input, and then 99, and it's just going to be 404, and that because it starts with a 4. Yes. So what did we say? 404 seems more right. What? We still got it wrong. Oh no. Oh no. Um, so we probably did our algorithm wrong. I'm not really thinking too closely about any of this right now. Of course. Come on. What we want is that will stop that from happening in the future. Okay, so we said it was 40. Total risk of this path is 40. And how do we look at it? We can say, a var, and while we called it p's or something, p's equal p's of c. We have two statements we want to do here. Right, so this will trace us back to 0, 0, 1, 2, 1, 2, 2, 2, 3, 4, 5, 6, 7. Wait, what? 6, 7. Oh, those are 4. And you know what? Let's just so we can keep track of what's going on here. G of n. Right. So 1, 1, 2, 1, 3, 6, 5, 1, 1, 1, 5, 1, 1, 3, 2, 3, 2, 1. Oh, yeah, and then plus the last one. Well, so we solved the sample data correctly. Total risk of any path from the top left to bottom right. I mean, what is there to say about it? Let's just make sure. Because all seems appropriate. The number, add up the result of each position you enter. Starting position. Leaving it as no risk. Yeah, okay. So what's going wrong on input? So 404, I don't really get what the problem here is. So the bottom right is 2. Is this? Let's just look at our input again. The bottom right is 2. And it seems pretty clear. So 5, 1, 1, 3, 5, 4, 1. I mean, this is all looking pretty reasonable. What are we doing wrong? Well, first let's give a closer read to the problem to make sure I understand what we're doing. Let's actually see if this is monotonic. 9, 7, 6, 5, 4, 3, 2, 1, 0. 8, 7, 6, 5, 4, 3, 2, 1, 0. 9, 8, 7, 6, 3, 2, 1, 0. 8, 7, 6, 5, 4, 6, 5, 8, 7, 6, 9, 8, 7, 6, 5, 4, 3, 2. So this is not crazy. I don't know what I screwed up here. I guess we have to think through what did I do correctly about this algorithm and what did I not. D's of V Oh, because this is a heap, of course. This is a heap. What am I thinking? Of course, it's a heap. It's. Oh. With the minimum distance. And I do have a heap at my disposal. Somewhere. I know all these things. I'm just very bad at doing things. So. Heap of 0.2. See, anyone who had this algorithm in a library nailed it really quickly. um, Q push V. Okay. We don't really need this, but it's fine. So what did we... no. Not that. If visit. If wasn't inserted. Continue, because that means we've already been there. How do we do this? Because we're reducing D. So how many? What are we doing? There are only 1,000. Let's, because we actually, the algorithm we just wrote, we need a Fibonacci heap for. So let's. Oh God, this is awful. So let's forget using a fancy data structure and brute force this. Visited. No. Okay. What a bad night. NG grid. Q insert V. Okay, now let's say Gee. No, we can't map. Oh my gosh. Zero, comma, that, min, 0, and now we're just, see, this is quite complicated code again. So, yeah, of course, visited. Don't need any of that. If point two, so that's on line 17 V. Nope. No, we don't even. I don't even know what I'm doing now. And how long? We've spent 40 minutes on this first problem. Just implementing Dijkstra's algorithm badly, over and over again. So, using a priority queue. Oh, this is actually what I should have been. Man. Yeah. Okay. Oh, okay. Okay. Well, we're starting over again. This is. Yeah. Okay. Oh. Okay. Prev is undefined. That's all good. We have our Q. Q insert V. Yes, yes, yes. That's working fine. While important that goes first. While that's not empty. For each neighbor, just to make it even. Not that it matters. If it's less than that, then and decrease. We need a decreased priority, really? Why am I making this so hard? Of course we need a Fibonacci heap for that. I do have a Fibonacci heap that I can use, but should I pull out my... No, there's got to be a way to do this without using a clever data structure. Dog, you're kind of in the way. Vertex and Q with minimum distance. I mean, we're just changing our mind all the time about what we're doing here, aren't we? Oh, I know this is going to drive everyone watching crazy, but I'm I'm tempted to start over again because I know I can implement this algorithm, right? I need to... So what's going to be slow? Because we ran it and it was slow was the problem, right? It was ungodly slow. So if we simply... Q is a set of points. Put all the points into Q, right? The distance of getting there. Okay. Oh, this is what we were doing before. 0 to 1 to 1 dot 0. if been here before, but I don't think any of this visited stuff is well. Okay. Visit teams. Yeah. Okay. Yeah, because that's going to be there. Okay, let's see how this goes. Oh, visited. Don't need that. Except we do. What's going on here? If it was not inserted. How did this start? Oh. Started, so V is that. Oh, but of course we need to remove it from Q, which we're not doing. Q, remove V. Oh, how are you? 34. The total is getting up there, so maybe we're actually making progress, and we're gonna get there maybe 407. But then do we subtract 4 or what? So we think there's a path that's of 403, don't we? Oh my God, what a terrible day. Yeah, oh. What is part 2? How can this get any worse? Because the thing is, this wasn't an interesting problem, is my main complaint about it. Okay, find your way out. 5 times larger than you thought. The area you originally scanned is just 1 tile. Repeats to the right and down are 1 higher. So can we brute force this, or is this going to be 25 times? I mean, see, now because we're slow, let's actually get rid of our prints and see how long this takes us. Yeah, see, this is going to be just astonishingly slow if we don't use a real data structure, right? So I guess we pull out a Fibonacci heap? You don't need a Fibonacci heap to solve these stupid problems. There's an easier way to do it. There are only two options at every point. There aren't that many neighbors. Well, we might as well give it a go, shouldn't we? Okay. Okay. Four. Plus 1. So it's from 1 to 9, isn't it? So it's 0% 9 plus 1. Right. 0. 0 plus 1 percent 9 plus 1, right? One, two, three. How does that work? And this is the wrong syntax because I'm just not a happy camper. 0 plus 2 parenthesize plus 2% 9 plus 1 plus plus 3. Big grid. What are we doing? We're so we do that, right? And then we do plus equals plus 1 2 0 no. Um, 1, 2, 3. 1, 2, 3. So 2 more. And that's oh, come on. I mean, so we should probably find our Fibonacci heap, I guess, and use that because I do have one lying around somewhere. Um, structures. I mean, there's a lot of code in this, isn't there? How is this going? Yeah, it's gonna take a while. So, what do we do here? Let's just. We're going to inject this textually above here. And how do we actually make a Fibonacci heap? And it's all, this is all based on less than, isn't it? Yeah, it's based on less than, greater than, all that stuff. What a huge pain this is, you know? Like yesterday, there must be a faster way to do this because you don't need such powerful data structures to do this stuff. But, yeah, FibHeap takes a comparable. So, what do? We have to say that a point is a comparable. Right? Oh, but they're not, are they? Because we have a 0.2 and it's hashable. So let's extend or point, right? Um, and let's read the book of words on how to write a comparable in, come on, in Swift. See, we're at an hour, and like as a rule, these things I like to give up after an hour. Come on, Apple. Swift Standard Library. Implementing comparable is what we're looking for. Conforming less than. Static func less. Okay. Turn these ba 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 is less than these right hand side. So, and if we say our Q is now a fib heap, how are we doing? Nope, no answers. Okay. And updaters, because in our Fibonacci heap, see, and people can't even read this because my text is so small, so we might as well make that bigger. Although this is a terrible video. And what does our Fibonacci heap return? If public insert. Oh, it returns a function that takes t, doesn't it? So, our updaters is a map from point twos to t's to void. Updaters of v equals q. Is it insert that we called it? Yes, insert. And then we do have pop. So, okay, while let v equals q pop. And we can get all that. The visited stuff is fine, I guess. That's fine. And then we have to do updaters of p. And we just give it p T again. How much of that compiles, I wonder? Oh no. 2 Fibonacci. Okay, very little of it compiles is the answer. Wait, why not? Synthesis is not automatic synthesis. Oh. Yeah, of course. So we need our 0.2. This needs to return a bool. How much of that does this solve? Some public cannot find var updaters. I thought we were doing so well asymptotically here. What are we still doing slowly? P is neighbors. Okay, pop is not. Oh, that did work. So 2840, because we still have to subtract the 4 because we're still that bad at these things. Yeah. Well, listen, we got to the finish line, but I feel terrible about just about everything about that solution. We threw in some incredibly overpowered library crap. I mean, we wasted all our time trying to build an algorithm from scratch and then realized that we needed a very efficient version of the algorithm. And so we had to just throw in this thing that I built a couple of weeks ago as part of a library, which was, it was only a couple of hours work, and that included, testing and everything at the time. But even so, I don't feel like we really solved that problem at all. I will probably have a think about whether there's a smarter approach to doing that than what I took, because I feel really lousy about how I solved it. So anyway, we got to the finish line, so that's something. I'll have a think, and I'll see you tomorrow. Bye.